Okay, so it is a pleasure to introduce the speaker of today, Alita Zibi from the University of São Paulo, which is going to talk about, I don't see the presentation here, but so I think I'll leave Ali to introduce the title. Thank you, Ali.
So, do everybody else see?
No, we're
not. No.
Ali is gone.
Oh, there you are.
No, we saw it before, but not now.
I don't know why. So let me just.
We saw that
Okay,
before.
I'm sorry. Okay. Maybe now. Okay, sorry, I was not transmitting.
Okay, on Margulis measured on foliations and measures of maximal entropy. There you go.
Good. Okay. So thank you very much, Regis, for introducing. I would like really to thank Lorenzo for invitation. This is a very nice tradition that he had created. I just counted, it is the version 23 of this seminar. So thank everybody also to be here this day. Okay. Do you hear me?
Yes, we do.
Yes.
Okay. So this work is about measures of maximal entropy. So let me go directly to some very brief history. Maybe in dynamics, we begin to talk about uniformly hyperbolic dynamical systems. So here we have the very celebrated measures, which are called Bowen-Margulis measures. Although I would like to emphasize today that the approaches are a bit different. So the approach and the philosophy of the Bowen result is to equidistribute periodic points to obtain a measure which maximizes entropy, and then he uses some specification properties, etc., and uniform hyperbolicity. And the measure of maximal entropy in this case coincides with another construction which was done by Margulis, in fact, in his thesis for another reason, to count the geodesic, the number of geodesics, etc. And in particular, Margulis constructed the measure of maximal entropy for anosov flows and also for uniformly hyperbolic dynamics. It was not written specifically, but the same proof works. And the idea is, again, to find a measure which is kind of uniform measure on the unstable and the stable manifolds of the dynamics. And more importantly, the dynamics acts linearly. So you have a reparametrization of your stable and unstable foliation in such a way that your dynamics acts as a linear map. Okay, and then for axiom A dynamical systems, you have Ruel-Sullivan. They have written these measures of maximal entropy in terms of product measure geometrically in the language of currents, etc. But I would like to say that in the approach of Ruel and Sullivan, they indeed use kind of symbolic dynamics. So you have Paris measures, so you have symbolic dynamics, so you have your measure of maximal entropy coming from symbolic dynamics, and then you show that really these measures have some geometric meaning on your lamination of a stable and unstable, stable and unstable lamination for your axiom A dynamics. So in this direction, talking generally for general dynamics, I would like really to advertise this result, which was which Omri talked about that. It is about general surface dynamical systems. So every C-infinite surface dynamics with positive entropy has at least has at most finitely many ergodic MME, measure of maximal entropy. And if it is topologically transitive, then you have uniqueness. So I put it exactly in these slides because, of course, it is a far-reaching generalization of symbolic dynamics ideas, but it uses really symbolic dynamics, but of course in infinitely many symbols and many other technicalities, of course. Now I go directly to the partial hyperbolic setting, which is my setting of this talk, and it is kind of beyond uniform hyperbolicity. So then there are many, many results. Maybe I will forget some people here, but I have to be objective to go directly to our results. So we have derived from Anassov diffeomorphisms. Essentially, they are you begin with an Anassov diffeomorphism and you go through a isotopy path, and then you have a partial hyperbolic dynamical systems. And in these results, typically center dimension is one-dimensional, and then you have the results of Raoult, and also then by Buzzi, Fischer, Sambarino, Vasquez. You have some results when you have center dimension divided into one-dimensional subbundles. Here you have existence results. So here, for derived from Anassov result, with one-dimensional center bundle, you have a complete result. Whenever you have a partial hyperbolic, so here one-dimensional partial hyperbolic with center bundle decomposed into one-dimensional centers, you have the existence always, so it is not necessarily derived from Anassov. And then I would like to talk some minutes about one-dimensional case, center case, whenever your center leaves are compact. And then I should mention a recent result of von Klimenhaga, Yakov Pezin, and Agnieszka Zelerovich, when they proved that in general, when you have some partial hyperbolic dynamics such that your center dynamics, your center bundle is kind of neutral. So neutral, you can guarantee neutrality. For instance, if the derivative is just one or less than one, for instance, less than or equal to one, or more generally, whenever you know that it is Lyapunov stable. So the center segments does not grow when you iterate by Fn. So there is some bound on the growths of the center list. So in this case, they prove uniqueness results for even equilibrium states for some general Holder potential for the dynamics. Okay, so but the problem is that, okay, you have this kind of neutrality on the center direction. Essentially, you can apply it for flow, of course, the time-bound map of a flow, because then you have derivative is equal to one, or some other dynamics. But when you perturb the flow dynamics, then you may have many dynamics which are not topologically neutral. Okay, so let me just announce our previous results. So I'm focusing on the partial hyperbolic dynamics. So the first result that I would like to recall is a joint result with Raoult and Federico and Hanna, when we proved that if you have a partial hyperbolic dynamics in three-dimensional manifold and it is accessible. So let me go to the complete announcement. So if you have a partial hyperbolic dynamics is accessible, dynamically coherent, and you assume that you have one-dimensional compact center leaves, okay, then you have a dichotomy. The dichotomy is either you have a unique measure of maximal entropy, and in this case, the central Lyapunov exponent is 0. So this is the non-hyperbolic case, or you have finitely many ergodic MMEs such that some of them are with positive Lyapunov exponent on the center, and some others, non-trivial number of them also, there is at least one which negative exponent. So these are, of course, ergodic measures. And maybe some important highlight of this theorem is that in the first case, when you have unique measure of maximal entropy, where your ergodic measure is non-hyperbolic, you can prove using a result which is based on Avila-Viana invariance principle, to prove that the first case is really rigid. Rigid means that you can have an action of the circle such that commutes with your dynamics. So the picture that you should have in mind is that your dynamic is kind of this dynamic kind of a skew product, for instance, and then these are the center leaves. So if you, sorry, do you see this picture now that I draw?
Yes.
Yes, we see it.
It is interesting because I don't see in my laptop, but okay, so that's good. So here you have the picture that you should have in mind. You have this skew product type dynamics, for instance, and if you have in the first case, then your dynamics is kind of rotation. Well, it's not exactly rotation, but you may have an action, isometric action of the circle, such that the orbits are the center leaves, and it commutes with your dynamics. Okay, so this part is really using Avila-Viana-Wilkinson rigidity result, but we should prove that this fits to this setting, in fact. Okay, and in particular, you see that generically you have hyperbolicity of the maximal entropy measure, as the first case is really easy to break after a infinite perturbation.
Ali, you insist
Yes?
that those measures, the hyperbolic measures, they don't come in pairs, so they can have different cardinalities?
Yes, they can have, in principle, they can have different cardinalities. Yes, you can assume some extra assumption, and then you prove that you have just one of each sign. But in general, you may have something strange with, I don't know. In fact, in general, I think you can, I'm not aware of any example with accessibility and all of these conditions, yes. But one of my students have done some results that show that you can construct of that cardinality or that, but equal numbers. Yeah.
So you don't have an example for different.
Satisfying all of these hypotheses, yes, as I know, yeah. I don't have an example. Yeah, of course you can kind of construct some product dynamics with Morse-Smale, and then you put, but then you don't have accessibility, you don't have, okay, all of the hypotheses. Very well. So I would like also to advertise just in this direction of these ideas, a result joined with Jiagang Yang. We proved that in the second case, so in fact, we proved an invariance principle using unstable entropy. So it is essentially says that if you have this kind of dynamics of the previous theorem, if the entropy of a measure along the unstable foliation, if it is equal to the entropy of the base, here the base is some Anasov, topologically Anasov dynamics. If you have this, you can put here a topological, okay? If you have the topological entropy of the base is equal to the unstable entropy of a measure, then you conclude that your measure is U invariant. This measure mu, when you disintegrate on the center leaves, is U invariant. So this is for experts maybe, but you can concentrate on the announcement that it is written here, is that in the hyperbolic case of the previous theorem, joined with Hanna, Federico, and Raoult, we can prove that, in fact, even high entropy measures are hyperbolic. So in the first look, you may expect that, okay, this should be the case, but it's not obvious to show that if you have any ergodic measure which has high entropy, then the measure should be also hyperbolic. So I don't see my presentation again. I hope that you see the presentation.
Everything is fine.
We see it.
Okay, so this picture here, so you see this picture here, this picture I put from Lorenzo, Katrin, and Micha Ram's paper. So this kind of idea appeared in the skew product dynamics also. in the IFS, in fact, iterated function systems. So this picture shows what was the idea of the thing that I am writing here. Here you have in the horizontal axis, you have the Lyapunov exponents of measure, Lyapunov exponents, and then on the vertical you consider the entropy, the supremum of the entropy of the measures with the same Lyapunov exponent. So this picture summarizes our result, which appears for iterated function systems also, and says that, okay, if you have high entropy, then your exponent also should be away from zero.
Sorry, Ali, can you tell
Yes.
me again what's the context of in which cases your proof with Jagan holds? For which
Yes.
diffeomorphism does it?
Yeah, exactly. I said in the same setting of our result. In fact,
Okay,
we prove
okay.
some general result by but here I'm applying in our setting setting of our joint paper. Okay.
Okay.
So
Okay.
in the second case you have this announcement.
Yes. Yes. Okay.
Yes. Okay.
Thank
So now I go directly to a different setting, which is, so you remember that we have this kind of classification of partially hyperbolic dynamics. In fact, this is a very deep project of classifying partially hyperbolic dynamics. And there are many people involved in this project. The question was raised essentially by Enrique Pujols and then improved and changed. And there are many authors in these conjectures. And the idea is that, okay, you have derived from Anasov, a skew product, and you have flow type dynamics. And then there appeared new examples. I will not go inside because I'm not expert of this classification. So what I would like to say, to advertise that, okay, now we have another category of partial hyperbolic dynamics where are important to understand their measures of maximal entropy. And these are, to begin, we begin with perturbation of time-bound map of the Anasov flows. Okay, so for instance, you have a negatively curved surface, and then you consider the geodesic flow and you perturb it. Okay, when you perturb time-bound map, so the result with Jérôme Bouzy and Todd Fisher, we proved the following. So this is the announcement. If you have a transitive Anasov flow and consider a C2 or C1 plus, it can be C1 plus for the moment, C1 plus dynamic, which is C1 close to the time-bound map of the Anasov flow. So we suppose that you have minimal stable and minimal unstable foliations, okay? So we know that this is a very long-standing result about the existence of, about the minimality of a stable and unstable foliation for these Anasov flows. I will comment a bit about that. But for the moment, this is the hypothesis. So every dynamic nearby, either, again, a dichotomy, either you have just measure of maximal entropy. Here it is not one yet, but it eventually will be one using results of other people. So either just you have measure of maximal entropy, which is non-hyperbolic, or you have exactly two measures of maximal entropy, one of them with positive and one of them with negative Lyapunov exponent. So this is the announcement of the result. And in the second case, your measures are Bernoulli measures also, okay? So I would like to talk about this result, but maybe first I will talk about some comments about the results, some improvements, etc., some questions. So the result, in fact, is written and proved for flow type dynamical systems. So I will talk about the definition of flow type, partially hyperbolic dynamical systems. But again, maybe for experts, this setting coincides, at least for 3D, it is written. And the higher dimension, I think Santiago Martin Chech has results in this direction, that These are exactly the discretized unanswered flows. These discretized unanswered flows are kind of triumph of these guys, Barthelme, Fenley, Frankel, Potry, in the classification of partially hyperbolic dynamical systems. Okay, so essentially discretized unanswered flows says that you consider a dynamics which is kind of center leaves are fixed and your dynamics acts like a flow which is topologically unanswered flow. So you have two foliations which are center stable and center unstable, and your dynamic acts like as an unanswered flow. So here is the definition of the flow type dynamical systems. Okay, a dynamical system is called flow type if it is partially hyperbolic, dynamically coherent, one-dimensional center, so I'm one-dimensional center, and at least, well, this is a very technical condition. It is satisfied for all discretized unanswered flows. You can imagine that by some kind of closing lemmas, etc., unanswered closing lemma, I mean, or it can be substituted by other conditions. But anyway, the most important thing is that the dynamics itself, F, is a sliding point along the center leaves by means of a flow which is topologically unanswered. So this is a flow type dynamical system. Okay, so in our definition, we don't assume that this F is an unanswered flow. Okay, it is just a flow, but okay, eventually it should be a topologically unanswered flow. In fact, it should be proved by somebody. Okay, anyway, so this is the definition of flow type partial hyperbolic dynamical systems, and then I would like to put some questions, comments. So first of all, this minimality condition. Of course, this minimality condition should be addressed. So first of all, I would like to say that this minimality condition of both stable and unstable foliation is in fact the case. It happens for open sets accumulating on the time-bound map. So this is kind of old result by Lorenzo, Christian, and Raoult. So Diaz, Bonatti, Ures. So you always can approximate on a map of this unanswered flow, which is not suspension. You can approximate by guys open sets where you have both of the foliations are minimal. And then, so here I just increase the size here. So here you have another new results, kind of new results by Hanna and Raoult, which says that, okay, maybe you don't have both of the foliations minimal, but in a neighborhood of the time-bound map, you have at most, you have just one minimal set for both foliations. Maybe this minimal set is not the whole manifold, but you have just one minimal set. This has been proved also by Sebastian Martin Cich and Nancy Gelman. Well, they have a very different approach, and they are working in other results too. So I put both of the references here. So you have at least one of these, you have just one minimal set. I'm emphasizing this because it is possible to work with this and improve our previous results, it will appear. So there is another important result in this direction, which is invariance principle of Crovissier and Poletti, which in particular shows that in this setting, the non-hyperbolic case is time-bound map again, and it is open and dense. So they prove some invariance principle such that it guarantees that the second case, well, the first case, in fact, of our result. So let me come back to the first case of our result. So the first case of our result, joint with Jérôme Bouzy and Todd Fisher, says that either you have non-hyperbolicity, all of the measures are non-hyperbolic, or you have just two measures of maximal entropy which are hyperbolic. So by an invariance principle, Mauricio and Sylvain can apply their invariance principle to show that, okay, the first case, in fact, you have unique measure of maximal entropy, and it should be Lebesgue along the center leaves, and you are rigid. So you are time-bound map of some flow. So your dynamics embed to a flow. So in particular, this shows that the second case is generic. So the second case, hyperbolicity, is generic. So generically, you have two measures of maximal entropy. Then you are close to time-bound map of a geodesic flow. Okay. So let me just make a very quick comment about symbolic dynamic approach also. So there is this symbolic approach which began maybe by Omri when he constructed this symbolic dynamics with infinite symbol and relating, and then a joint work with Bouzy and Courvoisier, which appeared in the talk of Omri. There is a generalization by Ben Ovadia in higher dimension. So he constructed this Markov partition, this symbolic dynamics for higher dimensional dynamical systems. So if you apply these Ben Ovadia results, you can prove that, in fact, your hyperbolic measures are Bernoulli. So here I commented another thing. I said that, okay, if you use this Ben Ovadia result, you can show that you have at most one measure of maximal entropy with negative or with positive exponent. But so if you have a measure of maximal entropy, two measures of maximal entropy with negative exponents, so you can use some symbolic dynamics and show that they are the same. This is because you have unique homoclinic class. So here you should remember or be the result of Sarig, Bouzy, and Courvoisier. But okay, this is far from answering our result about this dichotomy of the dynamics near to time-bound map. So you may have measures of hyperbolic measures, and you may have also zero Lyapunov exponents. So this cannot be addressed by this symbolic dynamics approach. Okay, so let me now, I go to my second part. I would like to give some ideas.
Ali.
Yes?
Ali, if I've been following you, are you saying that the symbolic approach shows that when you have the both signs MME, then it's unique?
Okay, it shows that it is written here. If you have at most one measure with positive, and you have at most one measure with negative exponent, but it doesn't rule out the existence of
two
non-hyperbolic measure. Yeah.
Right.
Yes, exactly.
But it says you have at most two hyperbolic, and then by Courvoisier-Politi you have exactly one, or at most one. Okay, thank you.
Exactly. You're welcome. So I would like also to I have another announcement. This announcement is a joint work in progress with Jérôme, Sylvain, and Mauricio Poletti. So here we improve much more the previous result, and we remove this minimality condition of the foliations. So okay, we lose some things. I mean, the measures are not supported on the whole manifold, of course. But here we use these results of uniqueness, the uniqueness of minimal sets for foliations. So Hannah and Raoult results, or Martin and Nancy results. So you prove that if you have a non-suspension dynamics, which is flow type, okay, then you can prove that then you have unique measure with non-positive Lyapunov exponent. So here if your measure is this unique measure, for ergodic, we mean ergodic. If it has negative exponent, then its support should be the unique U minimal set. So you have a unique minimal set for foliation. This is the unique minimal set, and your measure is supported there. Of course, you will have another measure which is positive. The Lyapunov exponent is positive, and it is supported on the unique S minimal set. And if you have zero exponents, then your unique measure of maximal entropy is supported fully and embedded to the flow. So of course, here you use the Mauricio and Sylvain invariance principle also, okay?
Do you have any assumption of minimality of the foliations in this, or do you prove minimality by this unique U minimal statement?
You don't need minimality, but you use here that you have a unique minimal set.
Okay, yeah.
Okay, so this is proved by people that I announced. Very well. So I should go forward. So now I change a bit, and I go to my title, which is Margulis family of measures. This is because the approach is kind of a project that we want to apply these measures, sometimes called transverse measures to foliation. And I would like to advertise Margulis family of measures also, because they are slightly different. And then we use these measures to address these problems, and it appears other problems that I would like to have time to talk about. So let me give the abstract setting. You have a foliation on your manifold. Then you call a family of measures on leaves, just a family of measures, which are radon measure, which are defined on the leaves. So it just depends the leaf. For any 2 points on the same leaf, you have the same measure. So the support of the measure is the leaf passing through the point X. And you want that these measures are locally finite, or if you want radon measures. So this is, for me, will be a family of measures on leaves of a foliation. And then we call it Margulis family. And here I need that the foliation is invariant by the dynamics. So the leaves are sent to leaves by the dynamics. Dynamics permutes the leaves. So the Margulis family is a family of measures where your dynamics acts linearly. So this was exactly the point that I talked in the beginning. So the action of the dynamics on these measures is just linearly. So there is a dilation constant here. This dilation constant for everybody who remember maximal entropy measures for hyperbolic dynamics, it is the exponential of the entropy, the exponential of the topological entropy effect.
So really, it has to be exactly linear? Exactly,
well,
for instance,
yes.
Gibbs measures, not examples of this.
Yeah, no, Gibbs measures are, yeah, I understand you. Gibbs measures have some Jacobian, and then, okay, for Margulis family, I assume this linear, but your question is very nice because, well, there is a developing result with my student Richard Cubas Becerra, when we generalize this to adapt for equilibrium states. So exactly as you expect. So you may have some Jacobian. So in literature, you have these measures, they can have Jacobian, as you said, okay, for Gibbs measure, for instance. So in general, you can have some potential and then you have some Jacobian. But here I would like to emphasize on linear because I go to the measure of maximal entropy.
Okay, thank you.
Okay, thank you. So let me just very quickly remember the transverse measures for foliations. So this area is very, very rich. Every day I see new results, and then you have these plant results. You have Ruel-Sullivan, but today is the commemoration for Sinai. We should also remember that Sinai also began these measures related to foliation. There is also results by Hersch and Thurston. So let me say you what are the transverse measures for a foliation. It is a bit different. So what is this? I will come back to these other references. So let me go. I have here a picture. So here you have two foliations. So you have two transverse foliation, for instance. So we will define the family of transverse measures for the foliation G as a family of measures on the foliation F. Okay, so if a transverse measure for foliation G will be a family of measures on the foliation F. Of course, you don't need a foliation F. You can just work with transverse flux. It is done in literature with transverse space, in fact. And then you say that, okay, a measure is a transverse measure whenever your measure on F is holonomy invariant, okay? I would like just to emphasize that when you talk about transverse measures, okay, you have measures on leaf of a foliation whenever it exists, of course. But the most important thing that to emphasize is that you don't guarantee any projective invariance of these measures. So what do I mean by projective invariance? So your measures are concentrated on the leaves of the foliation F. So if it is a transverse measure, means that by holonomy you send the measure to the measure. But the problem is that if you act the dynamics, okay, you need that your measure is something projectively unique. So this is not at all obvious. Whenever you have some ergodic foliation, you have some very strong hypotheses, you can guarantee this. But in general, of course, you cannot expect that results like plant results give you this kind of measures. They give you holonomy invariance measure, but we are addressing something more. Okay. Very good. So let me now go to a key proposition which relates these measures with measures of maximal entropy. So here is really the key proposition. So suppose that you have a C2 partially hyperbolic diffeomorphism. Okay. Suppose that you have somebody comes and give you a family of measures on the unstable foliation. And this family of measure is Margulis. Okay, it should have some measurability. You can imagine that you need some regularity, which is measurability. These measures vary measurably with the point. Okay, typically we find continuous measure, but not always. So suppose that this family of measure has some dilation factors. So the action of the dynamics is linear. Then what is important is that this constant controls the entropy along your foliation. So this is, I would like to say that this is the very first proposition which is useful for us. So this is kind of convexity argument. You can show this, well, Le Drapier type argument. You can prove this using the definition of n epsilon separated, etc. In general, you can prove that the topological entropy along the unstable foliation is less than logarithm of this constant. So what we are saying is that if somebody comes and give you a family of measures where your dynamics acts linearly, then of course this constant gives you an upper bound for the topological entropy along the unstable foliation. And the most important thing is that the equality holds if and only if your measure disintegrates along the unstable leaves exactly as your Margulis family. So here you have your unstable foliation, you have MUX, which is a measure which in principle you don't know anything where is come from. Maybe it is not coming from disintegration of some measure. It is just a family of measure. And then if you have a measure nu such that the entropy of nu is exactly the logarithm of du, then you know that your measure should be exactly mu. Your conditional should be exactly mu. Okay. So this is the relation of Margulis measures and the entropy. So here you see that I took variational principle to say that the topological entropy along the unstable foliation is less than or equal to logarithm of du. So this is a variational principle. Yeah.
Sorry, one more question. So,
Yes.
do Margulis measures, are they defined only up to dilatation?
Only what?
Are they, I mean, Margulis measures could be replaced by Margulis measures scaled by 2 and they'd still be Margulis measures.
Sure. This
So
is a projective.
when you say
yeah.
that the conditional equals mu, you mean up to normalization.
Yes, it should be understood appropriately. Exactly. This means
Okay.
that you take a measure of partition, then the normalized one or the same one. Exactly. So, is it okay? Okay.
Yeah.
Okay. So now I would like to address. There are many people, for instance, people from Hua and Wu, and there is a school of Chinese guys. Also, they are working very recently about these measures and entropy along the unstable foliation. So here, let me just make a comment. For flow-type dynamical systems, what is important is that the entropy along the unstable foliation is the same as the topological entropy, because you don't have entropy along the center, as they are just one-dimensional dynamics with bounded lengths. So here you see that the point is here understanding the dynamics on the unstable foliation, exactly. So this is why everything is U. And this made me to think about U maximizing measures. So to generalize these things, just going out of this setting of the flow type dynamics. So in general, you can prove that if there exists a Margulis family, mu, for some partially hyperbolic dynamics, okay? Then the topological entropy is exactly logarithm of the U along the unstable foliation, okay? So you see, we proved in the previous slide some inequality, that the topological entropy is less than or equal than logarithm of the U. But in the flow type dynamics, we ourselves proved that it is in fact equal. The topological entropy is equal to logarithm of the U. But I would like to put it in this abstract form of any partial hyperbolic dynamics. So if you have a partial hyperbolic dynamics, then you can ask about the existence of these Margulis families, and you have this equality. So maybe more importantly, you can remember a result. Well, okay, it is in particular written by Jiagang Yang, that the entropy along the unstable foliation, so here is unstable foliation, the entropy function is an upper semi-continuous. So just by analysis, you always have some maximizing entropy measure. So you consider any partial hyperbolic dynamics, not just flow type. So you always have some measure which maximizes the entropy along unstable foliation. So the question is that, does this guarantee the existence of Margulis family always? So this is not apparently clear that a measure which maximizing entropy, then it should be really Margulis family. It should disintegrate Margulis family along the unstable foliation. Again, here is general setting, not in the flow type. In the flow type, we have this result. So this makes me to really think about a relation between measures of maximal entropy along unstable foliation and measure of maximal entropy in the usual sense. So let me just formulate a very, very quick question here, which seems very easy to announce at least. So you have an anosov diffeomorphism. So you suppose that you have an anosov diffeomorphism. This is an anosov. So you can see your anosov diffeomorphism always as a partial hyperbolic dynamics if you have this decomposition. Then you can ask about this Margulis measure along here, Margulis. So question is that whether if you have a Margulis family on the strong unstable foliation, then it induces for you, it comes from a measure of maximal entropy. So this is kind of rigidity question. So the rigidity question is that if you have MUU Margulis family, does this come, comes from measure of maximal entropy of your Anosov diffeomorphism. So this is kind of, if you have, this is comparable with these results also, that if you have some measure which is Gibbs along the strong foliation, is it true that it is Gibbs along the unstable foliation too? I don't know any answer.
But
for
here
this.
you're not assuming, here in that question you would assume you have a measure whose disintegration is the bag, blah, blah. But here you're not assuming that the Margulis family comes from a measure. Is that correct?
Okay, yeah, you're right. What we have here, as it is an Anosov diffeomorphism, you know that your measure of maximal entropy disintegrate Margulis along the unstable leaves. Okay, so you have a measure which is Margulis along the weak unstable, which is Margulis, and somebody. So the question is that what is the relation between Margulis measures on the weak and the strong foliation? Yeah, this is, or do they coincide or not?
But I was just saying that you're not assuming that the Margulis, the UU measure, is a disintegration of a measure.
Yes, you're right.
In this question, right. Yeah, okay.
Yeah, you're right. But you can construct a measure. In fact, you iterate this measure using this usual Cesaro average. Whenever you have a Margulis measure on some foliation, whenever the dynamics acts linearly, then you can use exactly like U-Gibbs measure. You can iterate your measure, and then your limit measure is a measure whose disintegration is exactly your Margulis family. Okay, so you always can do this. In fact, like Pessin-Sinai SRB measures. So here you don't have any problem with the Jacobian and distortion because your dynamics is acting exactly linearly. Yeah. So let me just to go to the end of the proofs, almost to the end of the proofs, the results with Jerome and Todd. So what we proved is that we pushed this argument by Margulis. So we verified how was the method, and we adapted it for this general setting of partial hyperbolic dynamics. So you have, so I announce here in its general form, in its general form, if you have a C2 partial hyperbolic dynamics, you assume that it doesn't need even to be a strong partial hyperbolic. Suppose that you have this two invariant foliation. So as I said, in our result, we assume that Fs is minimal. So here you don't have in any U foliation in this general result of Margulis construction. So you need essentially that your stable foliation is minimal. Then you have a Margulis family on the center unstable foliation. So the picture is that if you have center unstable foliation and transfers to it, you have uniform hyperbolic dynamics. So here you have Fs. Suppose that this Fs is minimal, you can always construct these Margulis families. So observe that it is important that these measures are constructed everywhere. So this makes the things very different, this approach. And this makes this approach of Margulis families, in my point of view, strong. So you have, you don't have any almost everywhere. Of course, you don't have any measure a priori. So you construct on any leaf, on each leaf, these measures. They are holonomy invariant. Okay, holonomy invariant means holonomy is by a stable holonomy. And okay, they are full support in this case. As Fs is minimal, you can imagine that obviously these measures should be fully supported on each measure on each leaf, CU leaf. Okay, so the first abstract result in our joint work with Jerome and Todd is to construct this Margulis family. Very well. So how do we address these measures of maximal entropy? for this dynamics. So the idea here, so maybe first I give the idea here. The idea, even in the hyperbolic, in the uniformly hyperbolic case, is the following. You construct by hand your measure of maximal entropy, the candidate for measure of maximal entropy. So how do you construct? You construct it as a product measure. It's kind of, so you have here the measure on CU. You need a measure on S to construct a product measure on rectangles. So this is the idea. But the problem is that, as I said, by the previous slide, you construct the measure on the center unstable foliation. Okay, so observe that these measures are measures transfers to the stable foliation. So this is kind of, if you want to see this as Plante and the people on transverse measures, you construct transverse measure on the stable foliation. Now that's time to construct transverse measure to the center unstable foliation, which is measures on the stable foliation. Now there is some problem, because the transverse measure for the center unstable foliation is not easy to construct. So what happens here is that what you do, you construct your measure on the center stable, and then you induce a measure on the stable. So here I put center unstable to the unstable, but okay, in my picture here, you do first center unstable, then you need to induce a measure from the center stable to the stable. So the measure center stable measure is again using our result, and then you need to induce a measure on the stable direction. Okay, so this is not too difficult, in fact, and this uses extremely.
When you say induce, you mean like disintegrate?
No, I'm just saying, sorry, it's not disintegrating. I will comment about it right now. So you construct your measure, in fact, on the stable. Yes?
Your hypothesis, you don't have center bundle. You have only the stable and the center unstable. Then I don't know where.
Okay, you're right. In the hypothesis of that general result, we didn't have center. And now I'm saying to you how to prove the main result, which is strong partially hyperbolic. You're right. So here, maybe, yeah, here I have this one. And then I'm saying that, okay, you have both of these foliation by that results, and then I want to induce a measure on the stable foliation. And then the idea is you just you do it equivalently. I mean, you define your measure, taking any set on the stable direction. You define your measure, just the center stable, by pushing by your dynamics. So here you take any point. So let me just erase here. You just put any point, and here you go to the image of this point. So you see here, I'm using that the dynamics is flow type. So here it is important to be flow type. So as it is flow type, you can construct a measure just using your measure on the center stable dynamics. So by this process, you will construct a measure on the stable, on the strong stable direction. And these measures, again, are Margulis. This is easy to see because the center stable measures were Margulis, and it is defined just equivalently. Your dynamics preserves the foliations, and etc. Okay, so let me just this is, if you have a question here, the picture to show that why these measures are quasi-invariant. I'm just finishing my presentation. And these measures are invariant by holonomy. This is quasi-invariant by holonomy. So let me just summarize by a picture. What I did here, the following. I have measures on the center unstable foliation. These measures are invariant by the stable holonomy, but then you have measure on the stable leaves which are quasi-invariant. It means that the Jacobian is bounded from away from 0 and infinity. So if you construct, if you consider a set in the stable leaf, then to a stable leaf, you go by the center unstable holonomy, then your measure is not going exactly to the same measure, but you have a Jacobian. So of course it is not reasonable to expect that these measures are also invariant. In the uniformly hyperbolic case, it is the case. In the uniform hyperbolic case, you have two invariant by holonomy measures, but in the partially hyperbolic setting, of course, you, in this stable direction, you have just holonomy, bounded Jacobian, sorry. And why it is important? Because now you can apply Hopf argument to prove these uniqueness results that I mean in the announcement. So what is the end of the history? So in the end of the history, you want to prove that two measures of maximal entropy with, so here I have MS, here I have MS. Let me put it MU, I like, okay. So here you have MUX, and here you have MUY.
So
what happens is
we
that,
cannot see now, eh?
No, not
No?
yet?
I don't see, I don't know.
I see it. I see it.
I see it.
No, I see it.
I see
I
it.
see it.
Okay, sorry, I have some delay. Excuse me.
No, sorry. Okay, so I'm just very quickly going to give an idea why two measures of maximal entropy with positive exponents should be the same. So here is just Hopf argument. So how Hopf argument works? Here you prove that both of these measures should disintegrate to Margulis family. Margulis family. Okay, and then you know that your Margulis family is quasi-invariant. Quasi-invariant means that you can apply Hopf argument by the holonomy. So here you use a minimality also, and take two measures with positive exponent. Whenever you have two measures with positive exponent, you can conclude that you take generic points, and then you use center stable holonomy, and you prove that these two measures are the same. And you use that your disintegration are really given by measures which are where the holonomy has some bounded Jacobian. So this is the setting to apply the Hopf argument. I think that essentially, yes, I'm finished, and I thanks for your attention.
Okay, thank you, Ali, for your presentation. Are there any questions or comments?
I have a question.
Yes.
So Ali, this might be related to something you said earlier. If you have an anosol diffeomorphism with, let's say, two invariant unstable bundles, like the unstable is two-dimensional, but you have two invariant bundles, two further splitting inside the unstable. Do you have the disintegration of this Margulis family into two Margulis families with different scaling factor?
Yeah, this is in fact my question. So,
this is your question. Okay.
Yes. So you don't know. I don't know a relation between Margulis family on the weak and on the strong leaves. Yes. Well, I think that I should just emphasize that you should ask these kind of questions for Anasov, in fact, in the easiest situation.
Yeah, I'm asking for Anasov. Yeah.
It is good because if you consider, for instance, this skew product type dynamics, okay, that dichotomy that I said you can have, there exists measure mu, which is measure of maximal entropy, but it is not measure of maximal entropy along the unstable foliation, but not but not measure of maximal entropy along unstable foliation. Well, this is not exactly your question, of course, because here I don't have, I have here just a partially hyperbolic. Well, we can discuss it later maybe, but what I'm saying here that if you have some measure which sees the whole entropy, maybe if you restrict it on your strong leaf, then you will lose something. So I have an example. This is written in a survey that I have written it is online at arXiv. So you can construct dynamics such that your measure of maximal entropy, it is not U measure of maximal entropy. So in particular, your disintegration along the unstable, the strong unstable here, okay, is not Margulis. But it is not coming from genuinely anasoft diffeomorphism. It is partially hyperbolic. Yeah.
Yeah, I'm asking it for anasoft diffeomorphism. But...
Me too. I think that it is the correct situation. Yeah.
Are there any more questions?
Yes, I have some small comments. I think that the measures, the maximal entropy measures in our result, the question that Catherine asked, they come into pairs. For each positive, when one, you have a one with a negative exponent. They come into, they are, for each one, you have a opposite sign.
Well,
Yes.
I know that for each one you can construct another one, but okay, at some moment you should use accessibility, etc., because you can construct some dynamics where the number are not the same, of course. You just construct product with some Morse mail, but I'm not sure. I don't know. Maybe you're right. Yeah. I think that it should be true.
I mean, in more smell, the positive and negative come in pairs.
Yeah, exactly. So maybe it is. I think what we expect is that the number is exactly 2. So one positive and one negative exponents. So this is the expectation. In fact, it is proved to be true for nil manifolds which are not torus. This is a result of, if I'm not wrong, Jagang, Marcelo Viana, and Raul Ures. Jagang Yang, Marcelo Viana, and Raul. They prove that in all of the cases except for the torus, you have just 2. In the hyperbolic case, you have just 2 measures of maximal entropy, one with positive and one with negative. And it is very related to these topological results, because these 2 measures, for instance, the positive exponent measure is whose support is U saturated, and then you have just one minimal set again. For every nil manifold different from T3, you have just one U minimal set, and then you prove that, okay, you have just one measure. But as I know, up to my knowledge, we don't know for the torus.
Okay. I have a question.
But Hannah and Raul, one of you should turn off your microphone.
Yeah.
Sorry?
You're getting, Hannah and Raul are getting feedback because they're,
I see.
neither is muted.
I see.
Wait, what?
Sorry. No, I'm very interested in the question you posed to your students, so keep us updated.
Which question?
The one which considers the Jacobian instead of the fixed.
Okay, I can say you. It is not very secret, so it is the following. You can prove, it is written, you can prove that this Margulis family exists for potential. So what is the thing is that, okay, you have these Margulis families. So this is also, well, I skipped from one Pessin and Agnieszka result, but it is very related to their result. So if you consider this guy, the Jacobian of this thing, okay, what you expect is equal to exponential of minus phi of z on any point z, okay? So this is
Yes.
this is that you have, and then you again okay. What my student did is in its project is that okay, in the same way that we did with Todd and Jerome, you construct using Margulis approach. You can prove that there exist these measures for any Holder potential. And you continue to work a bit more to have more results that I think
Okay.
should have stopped. Yeah.
Excellent talk. Congratulations.
Thank you. Thank you
Are
to be
there
here,
more-
all of you.
Are there more questions?
Ali?
Ali, I have one question. It seems I will state it in a funny way, and then you explain what am I confusing or anything. The funny question is a Marguli measure a Marguli measure? Let me explain in the sense, consider take the Anosov two-dimensional one, and then because the way you define the Marguli measures are measures, they are defined in the whole unstable leaf, right? So when we have, let's say, the maximum measure, we know when we disintegrate in like the Markov partitions, we have this Marguli measure property you mentioned. So my question is, since your definition you gave of Marguli measures considering the existence of measure in the whole leaf, and it has to measure and it has to vary measurably, I wanted to know if like this Marguli measure defined in the Markov partition, it can be extended to, so we can get a Marguli measure in your sense. You know, because we know we could have the class in the leaf, but we have to pick it in a good way. So that's where my question is.
Okay, maybe Amy also had commented about that. So if you have Anosov, as you said, two-dimensional, you have the unique measure of maximal entropy. All of these things coincide. So what do we mean by uniqueness of Margulis family? So here, the Margulis family is unique in this case, in the setting that you asked. And the uniqueness means exactly projective uniqueness. It means that if you have two, so you talked about Markov partition, but you don't need ever to talk about Markov partition. You take any flow box. What I'm saying is that if you disintegrate your measure on the plaques, and normalize them, the Margulis families are normalized to a unique disintegration. So if you have two family of measures here in the Anosov case, both of them normalized one are the same. Okay, you can take Markov partition or whatever you want. I don't know if I answered your question.
Not sure. For instance, suppose you had in the Markov partition, can you extend in a measurable way? Because you wanted to find measure in the whole leaf.
I think the Regis question is about, yeah, you get your Margulis measure almost everywhere in some set, and you want to extend it. But what you have the stability by holonomy. So there is a unique extension in some sense.
Yes. Yes, in fact, okay, no, thank you, Francois, because it is related also when I said whenever you have these transverse measures, then you have measures on transverse plaques, and then you can extend it to a foliation if you have some foliation, which is transverse to your initial foliation. I think that if you have this holonomy invariance, then there is a unique way to extend. This is your point, Francois? So you use the fact that it is holonomy invariance. I don't hear him.
No, yes.
Okay.
Yeah. Are there any more questions or comments?
No, I also have a question. Ali, I'm not sure if I missed the point. You talked about the transitive Anosov flows, and then there are two cases about the central exponent. So are there examples where the central exponent, where there is an example where there are two measures of maximum entropy with opposite exponents?
Well, some referee asked for us also in our result, and there. So you may.
No confessions on Zoom. No confessions.
It's an obvious question, I suppose.
Yeah, exactly. So you may have non-transitive on-off flows, and then there are these Franks-Williams constructions, and then you may have more than one. Yeah.
The statement you stated was in a transitive case.
Yes.
Okay,
yes.
but so you don't have examples.
Example of what? I said you can use Franks-Williams to construct more than one measure.
Okay, sorry.
And then
yeah. Okay, yeah, I think I got it.
But if you okay.
Thank you.
I do have sorry, Lorenzo, you want to speak?
No, well, I have another question, but you can do your question first.
Okay. Mine is very, very, very naive. I think I missed I missed the role of the compactness, because for your flow types, partially hyperbolic systems, you ask for at least one compact center leaf. I don't see the role of what's the need of compactness.
Well, what I used, in fact, we used in this flow type is very essential, is the following, that you have here, the dynamic is like that. You have center foliation. So you need center foliation, which is fixed leaf by leaf. So the dynamics slides point along the leaf, okay? And what we want is that this distance is finite, it is bounded. So you have a continuous function from M to R. So if you have a compact manifold, this is bounded. It is uniformly continuous. So it is bounded. It is bounded as it is continuous, such that your dynamics is nothing more than fx tau of x. But as the manifold is compact, so this tau of x is bounded from above, okay, and below also. You don't have singularity. You don't have singularity, and you slide by a bounded amount of length along the center foliation. Does it answer partially your question?
Yes, thank you.
Okay. Well, but we use in the proof compactness many other times also, because we want to construct this product measure. We do it locally, and then we should patch on the manifold by finitely many foliated boxes. So there are some technical, essentially trivial use of compactness too. But of course, for non-compact cases, these Margulis measures, the measures of maximal entropy in Shapira and other people results appear. So it's not really, compactness should not be a very obstruction. In our results, in the way that I announced it, it is important.
Okay, thank you.
So really, I guess that the question is also about the existence of one compact leaf of the center foliation.
Well,
you need this.
In our joint result, so in the partial hyperbolic result with in this case, all of the leaves are compact. So what is your question? Or the manifold is compact?
When it is flow type, you said that you need one compact center leaf, I guess.
Yes.
Oh, okay,
yes.
okay. Sorry, Jacqueline. So if you, in the flow type, I asked for one compact leaf, okay? So this is, you always have this compact leaf. I understood compact manifold. So you have always one compact leaf for discretized on-off flow. So this is not a very, so why we use this? Okay, so I can explain for you very, very rapidly. We use this to show that constant of Margulis measure, this constant, is not equal to 1. So you need to show that this guy is larger than 1. Eventually you prove that it is exponential entropy, but it is a non-trivial constant. So whenever you have a compact leaf, then you can show that, okay, if I have some region, then it, as it is partially hyperbolic, I should come back and it accumulate on my compact leaf, and then you use the fact that your measure is locally finite. So this means that your constant cannot be equal to 1. Okay, if it is equal to 1, you take a fundamental domain, you come back you converge to your compact leaf, and then near to compact leaf, you have a region of infinite measure. So this contradicts the fact that our Margulis measures were locally finite. So did it answer your question? I think
yes, it did. Thank you.
You can assume other hypotheses to ensure that your Margulis constant is not equal to 1, which is not topological, but we preferred to put it in this way, as it is always satisfied when you have some discretized Anaso flow. Yeah.
Okay, thank you, Hao.
Ali, I have a question for you, but sorry, because the topic changed a lot. You comment these examples where the unstable entropy is less than the entropy of the method. Can you say something about the properties of that examples, or say something more
Yes.
precise? That is very complicated. I don't know, you are tired or not. So.
No, I hope that I understand your question. So what I said maybe related to when I answered Kadim, you mean, or another point?
Yeah,
because
the thing that you talked to Kadim.
Yes. So it is related to this this theorem with Raul and Hanna and Federico. So here you have measures. So suppose that you have two measures. You have one measure with one maximal entropy with positive exponent and one with negative exponent. Okay. So what I'm saying is,
I'm not hearing, Ali. Is anyone?
I guess
No.
that we lost
We lost that.
the connection with the link.
We'll come back.
Maybe he started to do many questions, you know. Maybe he needs some rest.
Example, I have an example of what you say, Lorenzo. If the maximum,
then go ahead.
if the topological entropy coincides for some reason with the metric entropy, and the center exponent is positive,
Yeah.
then the unstable entropy is strictly less than the topological entropy.
Okay, thank you. Well,
do you hear me?
Now, yes.
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 Now yes.
Yes. I think that Hannah answered my question, but thank you, Hannah.
Do you hear me?
Yes.
Yes.
Okay, I just switched off the iPad. So what we can prove is the following. In this example that you don't see any example here, maybe no.
I saw
Okay.
something. I don't know what.
Okay, what happens is that I have here another thing. So you see.
Yes.
I see
Yes.
The blackboard.
You see?
Blackboard. Yes.
Yes.
Okay, so you have, in this example, you have one measure with positive exponent and one measure with negative exponent. Okay?
Yeah.
And what you can prove is that this measure with positive exponent is not U maximal. It is not U maximal. This is not U maximal. So it is maximal for the dynamics, but it is not maximal for the unstable direction. This is just because if it were maximal with respect to the unstable foliation, by joint result with Jiagang, you can prove that this measure is U invariant.
Okay.
Okay. And as it has positive exponent, it is S invariant too. It is S invariant by invariance principle of Avila-Viana. And then if you have a measure which is both S invariant and U invariant, you can prove that in this setting it should be with zero exponent, and you get contradiction. So what is important here is that any measure which is maximizing the unstable entropy, in this case of one-dimensional center, it should be U invariant. The conditional measure along the center should be U invariant.
And as it has positive exponent, you know previously that it is also S invariant. And then you use these general arguments to show that it should be both S and U invariant, and it is the rigid zero exponent case.
Thank you, Ali.
Are there any more questions? Okay, so let's thank Ali for the great presentation. Thank you very much.
I